Alright, so we want to be looking at this section. What you want to do here is we're going to be looking at the constant velocity equations. And it's more like one equation, but it's kind of two equations at the same time, and we'll see why exactly I mean there's kind of one and kind of not really. What I want to do is take two approaches to this. I want to take the calculus approach first, and then I want to take the algebra, or not really the algebra, it is the algebra approach, but we basically assume something, right? Something that we learned in the past that I told you. But the calculus approach doesn't need any of that. It just needs to know what the derivative of certain functions are, what the integral of certain functions are, and that's it. So let's look at the calculus approach. Let me zoom in here. Oops, let me see. Where is my mouse? Not there. Okay, so I'm just going to do it here. So what the calculus approach is it involves making things that are true for every single thing of dealing with constant velocity. Oh, there's my mouse. There we go. So the thing that we have to look at is knowing that the velocity at any time is a constant, right? Constant velocity. Let's say the constant is v, and the reason why it's v is just because it's velocity. That's what I'm representing it as. V is always going to be the same no matter what t you plug in, right? T0, it's still v. T5, it's still v, right? And then the second condition is that we need to know its initial position, which I'm just going to write it as x naught, right? Initial position, not really too specific in any way. It's just a general thing. That's usually what the derivations usually are about. So let's see, we are not really given too much information here, so what can we even do with calculus, right? So this is kind of like, what power does calculus hold? And here's the power that it holds. The derivative of x with respect to t is v, right? Right, that's not a too difficult thing, right? I'm just rewriting it. Maybe you see what I'm trying to get at here. One of the things that we can do in calculus is solve differential equations. And usually differential equations involve a type of derivative. Here's the derivative. This specific type that we're trying to solve is called a separable, differential equation. Let's walk through the process of solving a separable differential equation. Our first step is to separate the dx and dt, right? They're usually thought of as a thing together, but now we're separating them. dx, I'm going to multiply both sides by dt, right? I separated them. That's always the first step of a separable differential equation. Now it kind of looks like, to me it looks like at least, a form kind of like part of an integral that's, we're missing something, right? We're missing the actual integral symbol. So there's the integral symbol. Kind of looks like it, right? So now we have to be careful of what we're doing it with respect to. We're doing x here and t here, right? They're different. So here. So now we find a thing and we get this, right? And then don't forget to add the c because it's indefinite integral, not a definite one. So now the next step is usually we have the integral thingy. Now we want to plug in the initial position, right? Initial position basically said that at t equals 0, x is equal to x naught. So let's substitute all those pieces of information here. X naught is equal to v times 0, which is 0, plus c, and therefore we get x naught is equal to c. Seems like we're not really doing much, but we actually are. So now we want to rewrite this thing with respect with c, what we just found as c, inputted in as it is. So x equals vt plus x naught. I'm going to write it like this, x naught plus vt. I'm just going to use commutative property, right? This is the equation. Second equation, the one that I was talking about being kind of weird, is just that the velocity is a constant, right? So the velocity will always be the same as the initial velocity you give it, no matter what, right? And this fact is just basically right here. This very first thing I wrote, right? This is something we just know for sure. With constant velocity, it has to be equal to something. It's going to equal to itself always. No matter what t you put, it's going to put the same. So Now we want to look at the algebra-based approach, and this one's actually much easier because, well, algebra is easier than calculus pretty much all the time. So we have to take a definition I gave a while ago. What defined velocity, right? Velocity was simply the change in position over time, right? Not a difficult thing. I'm going to rewrite this as the final minus initial over time, right? So let me just rewrite it as that instead. So let me move this right here, right? The next step is easy. Solve for x, not x naught. So solve for x. To do that, we just multiply by t on both sides, and then we get vt is equal to x minus x naught. In other words, x equals x naught plus vt. Not a difficult derivation algebra-wise, but we had to assume this first, right? This one we didn't have to assume it, we just had to use something really fundamental about it. And this is kind of like the idea of what we're going to do when we're looking at deriving a new set of equations called the constant acceleration equations. And then finally, one important note, this is all about constant velocity equations. In future problems or in future examples, we're going to be mostly focused towards constant acceleration equations. And the key difference here is that once there's a constant acceleration, we cannot use these equations anymore, right? Only for constant velocity. Constant velocity, that's really important. As soon as velocity is not constant anymore for any time period, we cannot use this equation anymore. It's basically invalid. It will make no sense anymore. So we'll look at constant acceleration equations, and when that's the case, these equations are basically, they don't make any more sense. But if we're talking about constant velocity, then it does make sense, right? It makes complete sense that these equations exist. So that's it for this video. The next video we're going to be looking at constant acceleration equations and deriving them.